All right, so today I wanted to go over the 2018 UIL Science District Test, specifically the chemistry section, and I'm going to try my best to make it as simple as possible. This test, I already did it. It's not too bad. There's a few acids and bases questions, which I see people get wrong or struggle on a little bit, but let's get started. So the first question says, how many grams of oxygen are in 424 grams of copper 2 sulfate pentahydrate? So we're trying to go from grams of one substance to another substance. And so that should tell you that we're going to be using stoichiometry, and we need to find how many moles of copper 2 sulfate pentahydrate we have so we can convert it to oxygen. So the formula for copper 2 sulfate pentahydrate is CuSO4 5H2O. And sulfate's a polyatomic ion. It's one you're expected to memorize, but in case you didn't know on this specific test, if you come down here, it actually shows you what it is right here. So that was a little thing I saw. But anyways, we're trying to get to moles, and the number of moles you have equals the amount of grams you have over your molar mass. So we have our grams, but we need to find what our molar mass is. So let's find the molar mass of this. So we have one sulfur, one sulfur, which is 32.07. We have one copper, which is 63.55. We have, let's see, 9 oxygens, so we have 9 times 16. And we have 10 hydrogens, which is just 10. And so that's our molar mass, but we want number of moles. So if we put our grams over this entire thing and we put this in the calculator, we will come out with, one second, 32.07 plus 16 plus 10. We will come out with 1.699 moles, roughly. And so that's our moles of copper sulfate pentahydrate, copper 2 sulfate pentahydrate. But we want grams of oxygen, so we need to convert this to moles of oxygen. So we come up here, we can do some dimensional analysis. So we have moles of that. We want moles of oxygen, and we want our moles of copper sulfate pentahydrate to cancel. So we need to find our ratio here. So let me rewrite the equation. I wrote it a bunch already. That's a 5, by the way. This should be a 5. So for every 1 mole of this, we have 9 moles of oxygen. And so we can come up here and write that as a ratio, and that should give us the amount of moles of oxygen we have, because these units will cancel out and we'll be left with moles of oxygen. But we want grams of oxygen. I'm running out of space here, but for every 1 mole of oxygen, we have 16 grams of it, because that's our molar mass. So those units will cancel out. Those units will fully cancel out, and we'll be left with grams of oxygen at the end. So if we take that and multiply it by 9 and 16, we will get 244.5 grams of oxygen as our final answer. And if we come over here, that's answer choice E. So that was just a pretty quick stoichiometry problem. If you know the formula, it shouldn't be that hard. Even if you didn't know the formula, it kind of gives you it down here. But next question saying, the diagram below represents a solution containing formic acid and formate ions, and it's asking for the pH of the solution, and it is also giving us the Ka. Sorry, I'm on my iPad, but it's also giving us the Ka. And so if you look here, it's giving us a ratio between our acid and its conjugate base. And if you notice that, you should be able to see that you can use the Henderson-Hasselbalch equation to find your pH. So the Henderson-Hasselbalch equation is the pH equals your negative log of your Ka plus your log of your conjugate base over its acid. Now the real equation has this as pKa, but P is just a function telling you need to take the negative log. For example, your pH is actually just your negative log of your hydrogen concentration. So in this case, we'd be taking the negative log of the Ka. So let's take our negative log, and we can just plug everything in already. So our Ka gave us as 1.8 times 10 to the negative 4 plus the log of, now we need to find the ratio between our acid and conjugate base. So we have 1, 2, 3, 4, 5, 6 of our acid, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Excuse me, 11 of our conjugate base. So we can come over here and just write that we have 11 over 6. And when you go ahead and plug that into the calculator, you'll come out with about 4.01. And it looks like it's answer choice B here. I messed up moved the paper a little bit. But, so yeah, it's kind of just testing if you know the equation or not. But if you do, it should be pretty easy. Also, I just erased our answers again. I don't know why I keep doing that. So the next question is asking, what is the oxidation number of chlorine atoms in Cl2? So you should know that any element in its pure elemental form has an oxidation number of 0. So the answer choice here is E. Now you might see Cl2 and think that's not a pure elemental form, but chlorine is actually a diatomic element, meaning it comes in pairs of 2. And so it's sort of just a definition question, but you should know that any element in its pure elemental form has an oxidation number of 0. So question 4 is asking, or it says the reaction A plus 2B yields C plus 2D proceeds according to this four-step mechanism. What is the role of compound X in this reaction? So let's see what compound X does. So it starts in our reactants at the very start and it gets used up, and then it's continued to be used up, and then it goes back to where it started. It's regenerated in the end, and then it's not in our final products. And so that means it's just used and regenerated again. And when a substance participates in the reaction, but it ends up unchanged overall, that's just the definition of what a catalyst is. So we kind of have 2 definition questions in a row, but they're pretty easy, so I'm not complaining. Next question says, if a 500 milliliter sample of gas at 25 degrees Celsius and 525 torr is heated to 323 degrees Celsius and allowed to expand to 1 liter, what will the final pressure be? So let's write our ideal gas law. What's changing here? Well, we can see that our pressure is going to change, our volume is going to change, and our temperature is going to change. But NR isn't going to change. So we can actually do this, and we can say PV over T will equal NR. And since this is a constant, this has to remain the same, even if your pressure, volume, and temperature change. So what we can do is we can say P1 V1 over T1 equals P2 V2 over T2. And I hope you can see why we did that. This is a constant, so we could have said that equals that and solve for it, and then we could have said that over that equals it, and then we just rearrange for NR. But anyways, we're trying to find our final pressure, so we're looking for this P2 right here. So let's rearrange our equation, and we'll get P1 V1 T2 over T1 V2 equals P2. And now it's just sort of plugging in until we get our answer. So our pressure 1 is 525 torr. Now let's put this in ATM. So 1 ATM, because that's just standard unit, is 760 torr. And so let's write that over here. So pressure 1 is 525 over 760. And then volume 1, it gave us as 500 milliliters or 0.5 liters. This is 1,000 milliliters in a liter. And then we're multiplying by temperature 2, and that says it's 323 degrees Celsius. Now we need to convert that to Kelvin, and the conversion from Celsius to Kelvin is 273. You add your Celsius plus 273. And then that's divided by our temperature 1, which it gave us as 25 degrees Celsius plus 273. And then our final volume, which it gave us is just 1 liter. So just multiply by 1. And when you put that all in the calculator, you're going to come out with about 0.691. And that's in ATM, because remember we converted to ATM. So let's come down here. No, that's 1 decimal place too high. Or that's a few decimal places too high, I'm sorry. And no, but we can see that some of our answers are also in torr. So maybe we need to convert back to torr. So like I said, 1 ATM is 760 torr. So if we just multiply our ATM by 760, we should come out with, let's take a look, it equals 525. And there we go, answer choice D. So just a gas loss question. You could solve it like this. You could say PV equals nRT, and you could just do it for one at a time and solve for what nR equal. Like I'm saying, you could take the pressure one, volume one, and temperature one it gives you, and you can solve for what nR would equal. And then you can plug that in to this equation it gives you, or to the second one. So you would, in this case, you would know what nR equals. And in that case, you can just rearrange for P2, and you can say P2 equals nRT divided by V2. But if you look here, if you sub in, you can sub this in for nR, and you'll come up with the same equation. You'll come up with the same equation anyway. So it doesn't really matter which way you do it. You just need to know what the ideal gas law formula is. And so if you look at a lot of these questions, it's really just knowing, it's really kind of just testing you what the formula is. But anyways, the next question is question 6. It says, what is the molarity of a 34% bi-mass strontium chloride solution? And it gives us its density. So in these sort of problems, you want to assume that you have 1 liter of solution, and then you can use the density to find how much mass you would have in that solution. So let's do that. So we have 1.3811 grams per milliliter of our solution. And if we're saying we have 1,000 milliliters or 1 liter, we can just multiply this by 1,000. And that'll give us the total amount of grams we have. So that's how many grams we have in solution. And so now we need to find the molarity of strontium chloride. So molarity is the number of moles over your volume. But if you remember, we set our volume equal to just 1 liter, so that goes away. So our molarity is just equal to the amount of moles we have in solution. And so really, all we need to find is how many moles of strontium chloride we have. And so we need the molar mass of strontium chloride, because moles equals grams over molar mass, and we have our grams here. So let's find out what the formula for strontium chloride is. Strontium is right here, chlorine is right here. So we'll have SrCO. Strontium has a 2 charge, chlorine has a 1. When you crisscross, you'll get SR1Cl2. And so for molar mass, we just need to add those up. So 87.62 plus 35.45 times 2. And when you put that in the calculator, let's see, you'll come out with about 158.52 as your molar mass. And so we need to remember that this question said we had 34% bi-mass solution. So only 34% of this grams is actually strontium chloride. So when we do our molar mass calculation, we need to do, or when we do our moles calculation, we need to multiply our total grams by 34%. And that'll make sure that we're not assuming that the whole solution is made out of strontium chloride. Because if we didn't add this, then we'd be assuming that our whole solution is made out of strontium chloride. But anyways, when you put that in the calculator, you get about 2.69 moles. But remember, our moles is our molarity, so this is actually molar strontium chloride. There we go. And 2.69 looks like it's answer choice D. So again, just not a bad question. You just need to know that in those types of questions, you can assume that you have 1 liter of solution, and that'll make it a lot easier. You could also assume you have 100 grams, but if you assume you have 100 grams, then it just makes, I don't know, it just makes things a lot harder, in my opinion. But that's another way to do it. So question 7 is saying an endothermic reaction that results in an increase in entropy is what? So we can see that our answer choices, they're all talking about spontaneous, and E is just, it's different from all the rest, but we can't assume that's wrong, but it probably most likely is. But let's start with these four first. So it's saying spontaneous, and when you see spontaneous, you should think of Gibbs free energy, which is delta G equals delta H minus T delta S. So this is your enthalpy, this is your entropy. And in an endothermic reaction, you need to remember that your enthalpy is always going to be positive. So this is going to be some positive number minus T. And an increase in entropy, when you do entropy, it's your entropy final, or when you do change in entropy, it's entropy final minus entropy initial. And if you have an increase in it, that means you're going to have a positive, you're going to have a bigger final than initial because you're going to have a positive change. So you're doing a positive minus temperature times another positive. So it's going to stay negative here. So really, you need to see that when you subtract these two numbers, whichever is biggest is whatever your sign is going to be. And delta G is spontaneous. A reaction is spontaneous when delta G is negative. So let's see. Is it going to be spontaneous at high temperatures? When you raise this temperature very high, this negative section is going to become a very big number, and it's going to overwhelm this positive section. So your delta G is going to come out to be negative in that case. So this looks to be the right answer, but let's see question B, or answer choice B. It says spontaneous at low temperatures. Let me rewrite this because I made it really messy. Remember, this is positive, this is also positive, so it's just the equation as it is. So at very low temperatures, this part, your negative part, is going to get very small, and your positive is going to be bigger. So your delta G is going to be positive, and that's actually not going to be spontaneous. So C is saying spontaneous at all temperatures. Well, we just saw that at low temperatures, it's not going to be spontaneous. Non-spontaneous at all temperatures, well, we already found that it's going to be spontaneous at high temperatures. And an equilibrium reaction, that just doesn't make sense. You can relate delta G to equilibrium. It equals negative RT. It also has like delta G is thermodynamics and equilibrium are really connected, but you can't really do anything with this right now. And we already found that A is true, so we can just say it's A and move on. Get rid of all this stuff because I'm just making a mess on this paper. All right, so 8 is saying the Lewis dot structure for the sulfate ion satisfies the octet rule, but is incorrect. Why is it incorrect? So the issue with this structure is it ignores resonance. In reality, the sulfate ion, it has multiple resonance structures where electrons are distributed amongst several sulfur-oxygen bonds. And these resonance structures, it lowers the overall energy of the ion and it stabilizes it. And because this doesn't give like a resonance structure, it's not the correct depiction. So it's actually answer C, but that like explanation wouldn't really help me. So you can actually use process of elimination on here, and that's what I used when I took the test. So let's start with E because on these tests, the chemistry director, he'll sometimes put questions like this. And you know, these are kind of just a gimme. You can just get rid of them, like because putting all the atoms in a line is just stupid. No. And let's read D. Because opposites attract, therefore the oxygen atoms will bond to the sulfur atom, not to each other. That just doesn't really make sense because first off, these aren't opposites. Sulfur and oxygen, they both have a negative charge. Yeah, they both have a negative charge. And so we can just get rid of that also. Oh. And B is saying because the formal charge on the central sulfur atom in this arrangement is not 0. Well, let's see. So sulfur has 1, 2, 3, 4, 5, 6 valence electrons. So it has 6 valence electrons. It has 4 unbonded electrons, and it has 2 bonds. So when you put this in the calculator, you actually get, or you don't need a calculator. When you solve it, it is actually 0. So answer choice B is just wrong. And then A says because it does not include the 2 extra electrons that give the ion a negative 2 charge. Well, can this go away? Guess not. Let's see. We just found that sulfur has 6 electrons and oxygen also does. So if we have 1, 2, 3, 4 oxygens and 1 sulfur, that means we should have 5 times 6, and we should have 30 electrons here. So let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So our structure actually does have the extra 2 electrons that give the ion a negative 2 charge. So A is also just wrong. So if you didn't know that it was C, you could just use process of elimination to figure that out. Or you could know that this ion is resonant in nature. I didn't, so that's question 8. So question 9 is saying a clear liquid is dispensed from a burette into a clear beaker and then weighed. The initial and final readings are shown in the image. If the mass of the sample is 22.42 grams, which of these liquids is it most likely to be? So we need to first find the volume because density equals mass over volume. And you might be wondering why I'm talking about density. Well, if you see answer choices like this, typically you can come over to our reference sheet and you can see that it gave us the density of all of these organic solvents. So it probably wants us to do something with density. And it also gives us that density as grams per milliliter in case you didn't know. But so the density here is going to be our grams divided by the volume. And the volume here is just going to be this volume that's given right here. So we just need to count how much space is in between these. So if we go, we can see that it's about, it looks like this is about 25 milliliters. And then right here, we have about 0.1, 0.2, 0.3. So I would say about 25.3 milliliters. Where am I going? And if we go on the calculator, that's probably not exact, but you can typically have a little margin of error on these types of questions. So when we put that in the calculator, we'll get a density of about 0.886. And let's see if that matches any of the ones it gave us. 886 looks pretty close to benzene right here. And so I'm going to go with A as our answer choice. And the reason it's not exact is most likely just because I didn't count this like as accurately as I could have. But again, you have some margin of error. So next question saying an empty metal glass cylinder or gas cylinder has a mass of 54 kilograms and a volume of 44.8 liters. When filled to a pressure of 32 atm with an unknown monatomic gas at 0 degrees Celsius, the total mass of the filled cylinder is 39 or 59.36. What gas is the cylinder? So what we need to do here is we need to find the number of moles we have first of the gas in solution, and then we need to use the amount of mass that it gives us that the solution takes to find the element. Because you remember, number of moles equals grams over molar mass. Molar mass. And if we're looking for the element, then we're going to be wanting to find our molar mass, because then we can just go check on the periodic table, you know, which looks like that. So we need to find grams divided by number of moles. And we already used the gas laws once, so let's use them again. So we have PV equals nRT, and we want to solve for number of moles. So let's do PV divided by RT here. So the pressure it gives us is 32 atm. The volume it gives us is 44.8. R is just the gas constant. It's on your equation sheet in case you didn't know it. And then the temperature it gives you is 0 degrees, but remember that's in Kelvin, so we need to make it 273. I'll do the 1.15 here. It shouldn't change much, but because we're dealing with kind of bigger numbers, I want to be as accurate as possible. And that'll come out to about 63.96 moles. And so now all we have to do is just plug in. So the grams it gave us, well, first we need to find. So the actual cylinder weighs 54 kilograms, but the filled cylinder is 59.36. So we just need to subtract these. And that'll give us the total amount of grams in kilograms. So we actually need to multiply that by 1,000 also. So let's put that in the calculator. You probably don't need to, but make it less likely for you to make a mistake. So it's about 5,360 grams. And we can divide that by our number of moles here. And that should give us our molar mass. And then we just need to go match that to an element on the periodic table. That gives us a molar mass of 83.8. And let's go see what around 83.8 exactly krypton. So it is good that I used the 0.15 because it gave us our exact answer of krypton. And it's answer choice D. Looks like I circled both. There you go. So the next question saying, if 85 grams of ice at 0 degrees is placed in a glass containing 425 grams of water at 15 degrees Celsius, what mass of ice will remain unmelted when the ice/water mixture reaches thermal equilibrium? So to start, we're gonna find the heat released when the warm water cools from 15 degrees to 0 degrees. So if you don't know, heat equals mc delta T, where C is a constant for whatever you're using. In this case, we're gonna be using water. And this will give us how much heat's released when we're going from our 15 degrees to our 0 degrees. So that's gonna be our change in temperature. But let's start plugging stuff in. So we have 425 grams of water. C for water is given on our equation sheet. It is 4.184. And our change in temperature, we're going from 15 degrees to 0. So our temperature final minus our temperature initial. Remember, it's a difference, so we can use Celsius. We don't have to add to Kelvin. And when we plug this in the calculator, we'll come out with negative 26,610, around there. And next we need to determine how much ice that heat can actually melt. So when you're doing a phase change, well, our ice is already at its melting point. So we just need to see that Q equals our mass times our delta H. And our delta H is given to us. This is the delta H of fusion because we're melting. So now we just need to rearrange for mass because that's what we're looking for. So Q divided by delta H will give us this mass. And we found our Q was 26,000. And the delta H it gives us for ice is 334 joules per gram. So let's go ahead and put that in our calculator. And that will give us 79.67. And it said we started with 85. So that's the amount that is melted. But we need to find how much remains unmelted. So we need to subtract 85 from this. So 85 minus 79.67. That's a 5. So 85 minus 79.67. And that'll give us 5.33 grams. And let's see. Answer choice. Looks to be around answer choice B. It's not exact, but it's since we're dealing with like these types of numbers, typically our answers aren't going to be exact, but there's a big enough gap between our answer choices that typically you can just assume that it's a rounding error as long as your process is right. So question 12 says a galvanic, I don't know how to say it, is constructed using magnesium electrode and 1 molar magnesium nitrite solution, and a silver electrode and a 1 molar silver nitrate solution. What is the standard potential for the cell at 25 degrees Celsius? And so it gives us our reduction potentials up here, and the species with the more positive reduction potential is going to be reduced. So our silver ions are going to gain their electrons, and because they're gaining electrons, magnesium is going to lose its electrons and it's going to be oxidized. And if you remember anox in a red cat, it's a mnemonic to remember that oxidation in these cells happens at the anode and reduction happens at the cathode. And because our standard cell potential, so E for our cell, will equal the E of our cathode minus the E of our anode. And we just found that our cathode is silver because it is gaining electrons, and it's reducing. So we can plug in our 0.8 potential minus our negative 2.37. And when we put that in the calculator, we'll get a standard cell potential of 3.17, which looks to be answer choice C here for question 12. Okay, so Again, not that bad. Question 13 says, a chemist dissolves 36.76 grams of calcium chloride dihydrate in a 100 milliliter volumetric flask and fills the flask to the mark. She then pipettes 5 milliliters of the solution into a 25 milliliter volumetric flask and dilutes the mark with water. What is the chloride ion concentration in the final solution? So first, we're going to want to find the amount of moles of calcium chloride dihydrate we have. So we have calcium chloride. Calcium has a charge of 2, chlorine 1, so we need to multiply here by 2. Dihydrate, so we just have 2 H2O. If you remember from question 1, hydrate's just the water molecule. So we need to find the amount of moles of this we have. So let's come up here, and let's find our molar mass. Get rid of some of this so it doesn't look as messy. So calcium, we have 1. Calcium has a molar mass of 40. So we have 40.08, that's a terrible 4, plus 2 calcium, or 2 chlorines, so 2 times 35.45, plus 2 water molecules, so we have 4 plus 2 times 16. And let's go ahead and put this in the calculator. And that'll give us a molar mass of 147.98 grams, actually. And so now we need to find how many moles we have. So it's given us this amount of grams. So let's take our molar mass and let's find our number of moles. Because remember, number of moles equals grams over molar mass. Okay, there we go. And that'll come out to around 0.248, but I'm just going to call it 0.25 moles because it's going to make the math a lot easier here, and we don't really need to be too precise in this question because you can see our answer choices are pretty decently far apart. So next, it's dissolved. It says it's dissolved in 100 milliliters, meaning our molarity is actually, or well, our molarity equals the number of moles over the volume, and we found our number of moles is 0.25, and our volume is 0.1. So we actually have 2.5 molar. And now we need to find, well, we're looking, oh, not molars, but we're looking for our chloride ion concentration here. And if you see here that we actually have 2 chlorine in our equation. So we need to actually multiply this by 2 because when when this dissociates in water, we're going to have 2, it's going to form, each unit of that is going to form 2 chloride ions. So this is our molar of our calcium chloride dihydrate, but again, when it dissociates, we're going to get 2 molar or 2 chlorine ions for every 1 molar of this. So we can multiply this by 2, and we actually have 5 molar of chlorine. And now we need to do the dilution, and so we can set M1 V1 equal to M2 V2. And now we just need to solve this, and when we do that, we will get 5 times our volume, which was 0.1, I believe. So come over here, do 0.1 must equal 0.25. We're putting, oh, no, I'm sorry. She pipetted 5 milliliters of that into here. So this is 0.05. Oops. And that equals x times 0.025. And when we solve for x, we will get this. And when we put this in the calculator, let's see what we get. If you can do a bit of mental math, you should already see what it's going to come out to, but I'll put it in the calculator just to be sure. And, oh, I'm sorry. I did this should be an extra 0 here, but this will come out to 1. And if we come to our answer choices, answer choice D is 1 molar. Okay, so again, it's just another, this question's kind of scary because there's a lot of stuff it's giving you, but as long as you know the process, again, it's not that bad. This is in the M1 V1 equals M2 V2. That's another formula you probably should know. It's using a bunch of dilution problems, but moving on. Question 14 asks to rank these single bonds from least polar to most polar. And so bond polarity depends on the difference in electronegativity between the atoms. And that means like on your periodic table, electronegativity increases like this. As you move to the right and up, you increase your electronegativity, and you want the greatest difference of that for the most polar bond. So let's look at what we have. We have carbon and oxygen, hydrogen and fluorine, phosphorus and sulfur, and bromine and bromine. Well, if you can already see here, these are the same element, so they're not going to have any difference in polarity. So we can automatically say that this is last place, and so A and B are automatically wrong. And now if you recognized hydrogen and fluorine here, well, fluorine is all the way up here. It is the most electronegative element, and hydrogen, it's not very electronegative at all. And when hydrogen bonds with nitrogen, oxygen, or fluorine, it actually makes a special bond or a special extremely polar bond known as hydrogen bonding. It's not actually a bond, but it's known as hydrogen bonding, and it is the strongest type of intermolecular force here. So it's going to be the most strong by far. So we can get rid of C also because it doesn't have our hydrogen bonding in first place. And next, we just need to look at the difference between carbon and oxygen and phosphorus and sulfur. So if we come over here, carbon and oxygen, its difference is this much, and phosphorus and sulfur are right next to each other. So as you can see, since there's a gap with nitrogen in between carbon and oxygen, it has a larger electronegativity difference because they're farther apart with that trend. Because if you remember, the trend is as you move to the right and up, you gain more. So while there is a difference here, this difference is bigger. And so it'll be more polar, and therefore it's going to be answer choice E. And so moving on, question 15, it's going to be a Hess's law problem, and it gives us this information and it wants us to calculate the standard molar enthalpy of formation for iron 2 ox O3. So, or iron 2 oxide. So what we need to do here is formation. So formation means that it's going to end up on the right side eventually, and that standard molar enthalpy means we only have 1 mole of it. So let's start by trying to cancel out some of this, because we only need its constituent elements that make it up. So that means we can't have this other element, this intermediate, in there. And so to do that, we can treat this like a math equation and treat this like an equal sign, I guess. So if you've done systems of equations before, if you multiply this whole equation by 4, right, and you'll get 12 and 8, and you'll multiply this by 4, you can end up canceling these two out. And so let's do just that. So let's multiply this entire bottom equation by 4, and that'll multiply our delta H by 4 also. And so let's go ahead and see. When we do that, we'll end up with 6Fe2O3 equal. We'll keep the equal sign because it'll make it easier to sort of visualize. And so we multiplied this by 4, so we have 12 iron. And then we multiplied this by 4, so we have 8 oxygen, plus this 1 oxygen, because we're adding down, remember? So we have plus 9 oxygen. And our delta H for this, well, we need to add our delta H's. So we'll take our 471.6 plus 4 times 1118.4, and we'll come up with a delta H that equals 4945.2. But remember, we only want the standard molar enthalpy, which means we need 1 mole of this. So we need to divide this whole equation by 6 now, and that includes our delta H. So when we do that, we'll be left with iron 2O3 equals 2Fe plus 3/2 O2. And we also need to divide our delta H by 6. So let's go ahead and do that too. And that'll leave us with 824, 824.2 as our delta H. But remember, we're looking for the enthalpy of formation. This isn't being formed here. So we need to actually flip this equation to 3 over 2 O2 plus 2 Fe yields Fe2O3. And when we do that, we just flip the sign of our delta H and it becomes negative. And so this is our final delta H, which looks like it matches answer choice B. And so in these types of problems, you can sort of just treat the whole thing like a math equation. You don't really have to treat it like a chemical equation, which is pretty cool. But question 16 saying, or asking, what is the concentration of nickel 2 plus in a saturated solution of nickel 2 phosphate if the KSP for nickel 2 phosphate is given? And so what we need to do here is write the disassociation equation. So first we have phosphate with it, which is PO4 with a 3 minus charge. And so when we balance our thing, we'll get nickel 3 PO4 2. And the disassociation of that is going to give us 3 nickel 2 plus ions plus 2 phosphorus 3 minus ions. And now we can do a Rice table. Oh, what am I doing? Just get rid of this. So this is a solid. So it's not going to be changing at all. These are aqueous. And we're starting with 0 of them. So we can say that our solubility is S. And that means that the change, when this dissociates, this is going to change by 3S. And this is going to change by 2S. And so if you remember, when you write Ks, you write it products over reactants, but you exclude solids. So we'll have our concentration of nickel 2 plus, but remember it has a 3 coefficient, so we have to cube it, times our concentration of phosphate, which is PO4 3 minus, but remember we have to square it because it has a coefficient of 2. So this is what our KSP is going to equal. I know my handwriting's really bad, but now we can just come over here and say our KSP times 10 to the negative 32 is going to equal, well, we just found that our concentration when it dissociates is going to be 3S. So we're going to have 3S cubed times, that's not cubed, times 2S squared. And now we need to do a little bit of algebra. So we'll come up with 27S cubed and 4S squared. And that's going to come out to 108S to the 5th, I believe. And that's going to equal our KSP here. Because we're solving for S so we can find our total. So we can find like our final concentration. Because 3 times whatever this S is going to equal our concentration of nickel 2 plus. So now we just need to solve for S. So S is going to equal 4.74 times 10 to the negative 32 divided by 108 and the 5th root of that. It's just a little bit of algebra. Shouldn't be too bad. But let's go ahead and put this in the calculator because I'm not doing that in my head. And that'll come out to 2.13 times 10 to the negative 7. But remember, our nickel concentration, you see, that's answer choice B right here, but or C. But remember, our nickel concentration has actually 3 times that. So we need to multiply this by 3 to get our final concentration. And so that'll come out to be 6.39 times 10 to the negative 7 as our final nickel ion concentration, which looks to be answer choice A right here. Okay, so it's just a disassociation thing. You need to know how to write your KP or your KSPs, and you need to know how to write the disassociation of a solid. But moving on. Question 17 says chlorine gas reacts with chloroform to form carbon tetrachloride and hydrogen chloride gas in this equation. The following time and concentration data was collected from this reaction. What is the average rate of this reaction? Well, if it gives us our time and our concentration, to find the rate of reaction, we just need to do the change in change in concentration over our change in time, or delta M over delta T. And so we can see that this is just point slope form. We just need the slope of this line, basically. And that should be fairly easy to do, because all we have to do is do y2 minus y1 over x2 minus x1, or 0.374 minus 0.167 over 148 minus 7. And when we put that in the calculator, we will get 0.00015, 147, I don't know how many places I went to. Yeah, 147. And there we go. That's choice C. It's a pretty easy question. You just need to take your values from the table and find the slope of that line, because the rate is just the change in concentration over your change in concentration over your change in time, or delta M over delta T. So yeah, fairly simple question, but again, moving on. Question 18 says, what is the work function of a metal? Well, if you've taken physics 2, or you know about the photoelectric effect, then this is just a definition question, and it's just something you need to know. It's a concept in the photoelectric effect, and it just refers to the minimum energy required to remove an electron from the surface of a metal. And so answer choice A is going to be our answer here. Again, it's just a definition question. It's just kind of something you need to know. And yeah. So question 19 says, when this equation is balanced, what is the sum of the coefficients? So this is a redox reaction, and we need to separate it into half reactions. So we have our gold 3 plus here. Let's see what happens with our gold 3 plus. When our gold 3 plus is in the reaction, it becomes gold solid. So this is going to become gold solid. And to do that, we need to get rid of this 3 charge. So we need to add 3 electrons here, because these electrons are going to cancel here, and they're going to leave us with just our gold solid. And now let's do the same for our iodine. And so iodine minus is going to become I2 solid, right? And so to do this, we need to add 2 electrons to our the second half of our equation. And you might say, why not 1? Like, why is it not 1 to 1? Well, because it's I2. So it's got twice the oh wait, I'm sorry. I messed up here. You need to actually balance this first. So you need to add a 2 here. So 2I2, because you have 2 iodine. But anyways, you need to add 2 electrons here. And that's what I was sort of getting at. Because it's I2, you need to change the coefficient in front of here to equal that 2. But typically, and you know, our chemical equations, we don't have electrons shown. So we need to cancel out these electrons. And like we did with the Hess's law thing, you can sort of treat these chemical reactions like a math problem, where they'll cancel out if you treat it like a system of equations. Also, this should be 2, but it'll cancel it out if you treat it like a system of equations. So we need these to cancel out, and so we need to make them the same, and we'll do that by multiplying this whole equation by 2 and this whole equation by 3, so we can get our electrons to equal each other. So when we do this, we'll get 2Au3 plus 6 electrons becomes gold solid, or 2 gold solid. And that's our first equation. I don't know why I drew a line, but that's our first equation. And then we multiply this bottom one by 3, so we get 6I minus becomes 6 electrons plus 3 I2 solid. And then our electrons are going to cancel out, and we're going to be left with 2Au3 plus 6I minus. It's going to become 2Au solid plus 3I2 solid. And our question asks us to find the sum of the coefficients. Well, here we go. 2 plus 6 plus 2 plus 3 comes out to 13. So our answer is going to be answer choice C. So it's just a little redox reaction question. Sorry about the little mistake I made, but You just need to know how to balance these sort of things by balancing your amount of electrons. And the final problem, it's asking about the molar mass of a diprotic acid. It says determine the molar mass of an unknown acid, H2A, if 12.11 gram sample of acid requires 38.38 milliliters of 5 molar sodium hydroxide to neutralize it. So first, we're going to have to calculate the amount of moles of hydroxide that we use, or the sodium hydroxide that we use in solution. So to do that, well, we know that molarity equals the number of moles divided by volume. So the number of moles we have is just the molarity times the volume. So we'll take our 5 molar times our 0.03838 milliliters, and that should give us the number of moles we have of acid, or of base that we titrated with. 0.03838. And we're going to come out with 0.1919 moles. But you need to see that this acid here is diprotic, which means that each acid molecule, it reacts with 2 hydroxide ions. So the moles of acid is actually going to be half this amount. And that's because it's because that we have H2. So we need twice as much hydroxide to neutralize it. So we need to divide this by 2 because that's the amount that we actually neutralized. So if we divide that by 2, we're left with 0.09595. And that should be the molar of our, what's it called? That's the molar of our acid. And it says that we have a 12.1 grams. And so if we just take the moles of acid and we take 12.11 divided by our mole here, we're going to be left with, let me see, let me put it in the calculator. 9595. That's going to come out to be 126.21, which looks to be answer choice D there. And so there we go. That's the end of the test. Again, this one wasn't really too bad. You kind of just got to know a few equations and then a few polyatomic ions, but really it's not too bad. I mean, yeah, thanks.